I'm very excited to be here. Thank you all for coming. So this is the first talk that I will be giving for work which is currently under submission to IQ. So you all are my guinea pigs. So please point out typos. Um, this is a talk about an architecture. It's an architecture inspired by some tools in computer graphics. And I'm going to spend a little bit of time motivating why we need to search for architecture. I suspect many of you already understand this. And then tell you about the model and why we're excited about it. So these are my sort of perspectives. First is that the role of machine learning architecture recently in some of the bigger problem disciplines like language modeling or image generation, the role of architecture is actually kind of underappreciated and has opened many of the practical doors for actually improving the scale of these models. And in this work, we target, I guess this last bullet point, I say computational science, which is like a massive domain with many, many, many problems. So we don't really target all of that. It would be a disservice to say so. This is more so a talk about something called physics-informed learning or inverse problems with residual minimization. So sort of large-scale inverse problems in computational science. And just to give some examples of architecture, I'm going to speed through these, but I would say the first big example of this is the residual neural network. It was responsible for drastically improving the performance and the scale of our ability to classify images, and this was around 2015. Next, I'm curious if you all are familiar with the UNet architecture. Good. Okay. This is the backbone of every diffusion model. It has barely changed since it was introduced.
Not anymore, no. We cannot put in
vision transformers is also this. But still, I mean, even today, you have these UNet architectures that are responsible for image-to-image functions, and they were originally introduced in the context of segmentation. And of course, the transformer architecture is not much to say here. I'm certainly not the most qualified person to say it in the room. But the transformer architecture has recently received lots of attention, to these points. This talk is about a very, very simple splat regression model. If we inspect it, it's already quite similar to a standard kernel regression model. The difference here is that, so in kernel regression, you have something like a Gaussian distribution. This is your kernel. There is a fixed bandwidth. In other words, you have Gaussian kernels with a scaled identity covariance. And really the twist here is that we will have anisotropy. So this is actually very simple. You can even also view it as a two-layer neural network. So I get this out of the way because otherwise you'll be underwhelmed. But to motivate this, I'm going to start by telling you our inspiration from the computer graphics literature, and then our goal for this project is to take some of these very, very, very performant algorithms and graphics and understand, like, what is the model, what is the algorithm, how can we generalize this and maybe replicate the successes in some other low-dimensional modeling problems. So this is an example of the output of the Gaussian splatting model. So this is a 3D scene being rendered. And in order to perform the rendering, there is a illuminance field represented by a model of the type that I showed you, a splat model. So this work was actually developed at INRIA in maybe 2021 and led to, I hope these are visually impressive rendering results. And you should imagine that the illuminance field is, for example, like a highly discontinuous function that carries the three-dimensional shape of the bicycle, the spokes of the wheels, the trees, the leaves, the stems. So really here we are already seeing a very, very, very difficult modeling perspective if you think about it from the perspective of like statistical learning. And this is an inverse problem. So in order to generate this data, you begin with a data set of images annotated by camera position. Typically, this is highly oversampled, and you use something called the radiative transport equation to compute how a camera would render a scene if you knew the illuminance of the scene. And so you solve an inverse problem by residual minimization, and that's how we recover these extremely complicated and detailed spatial fields. So this has been called, this architecture is regarded as the transformer of computer graphics. This is from, so this is just a slide to drive this point home. This is from the efficient splatting tutorial at CVPR, given by famous people at FAIR. I mean, this architecture has really changed what is possible in computer graphics. Okay, so what do we do in this work? We write down a general purpose splat regression model. We sort of explore the toolkit that's available for designing algorithms to solve general purpose inverse problems. And we give a little bit of theory, so basic approximation theory, and some semi-toy experiments just to explore this model. And of course, I have, for this particular audience, I think something especially appetizing about this is that it is a two-layer network. And those of you who are familiar with the mean field theory will see many simulations, many similarities between our setup and that. And there's no theory to practice gap. Right. So first, I just make a little comparison. The second row here is similarities. They're both two-layer neural networks. And in fact, for the uniform approximation theory that I won't say too much about it, but already this splat model is in the context of Sybenko's original result, famous result on uniform approximation of continuous functions. Some of the differences qualitatively, so mainly what you have in something like a ReLU MLP, you have what I call global activations. So this means that each neuron is going to contribute to the output for a set of inputs that is somehow global in the space. In this case, it's a half space. Whereas in the splat model, typically you have a sparse activation pattern. So only over a few splats are active, or in other words, there's very little overlap of the supports of the splats. And so we say that the activation pattern is sparse because there's only a few neurons that will be active for any given input. And so this is key for something like in the rendering context, you use something like a KD tree to pre-compute which neurons will be active, and then you accelerate your inference and you accelerate your training by using sort of like inference time sparsity. So there are already some like useful properties here. And there's the second point. So a lot of the talk, actually, we take a perspective for these models that is based on Wasserstein gradient flows. So when I say here BW manifold, this is the Perez-Wasserstein manifold, and sort of, if you take away anything from this talk, I hope it is at least like a general understanding of how, like, what is Perez-Wasserstein, what is Wasserstein gradient flow, and what is dynamical optimal transport. So, dynamical optimal transport is it's a tool for analyzing iterative optimization, but for probability distributions. So, for example, this is very useful in sampling in the theory of diffusion models. For example, it can be cast as dynamics in the space of measures. And to describe this, sort of the general things that you need is a pseudo-Riemannian structure. So our manifold will be the set of probability distributions. And then what I tell you about is the choice of tangent vector and the metric on the manifold. And this is how we will define gradients in the space of probability measures. This is eventually how we will train this model. Okay, so Wasserstein 2 geometry, this is our first option. So here I take a base manifold M. Script P is the set of all measures on that manifold. So probability distributions, you could think of M as RD. And to each distribution, we give a tangent space, which I'm not expecting this technical definition to be familiar to anyone. Well, this doesn't make sense unless you've seen it before, but roughly speaking, I thought the allowable direction that I can move when I add a measure under the Wasserstein geometry is the direction that can be realized by transporting particles. This is the upshot below. So I'm going to infinitesimally apply push forwards to the measure, and in that way I'm transporting particles. So this is my picture. So on the left in measure world, if you want to take a step along a tangent vector from mu0 to mu epsilon, then the nice thing about Wasserstein geometry is that tangent vectors in the Wasserstein space correspond to vector fields in the base space, is the idea. So you sort of have this lifting where a vector field in the base space is transporting particles, it assigns velocities to them. And this is just one tangent vector, one direction that you can move your probability. So this is Wasserstein geometry. Actually, any questions? Okay. So a specific case of this is useful for our formulation of splats, like splats themselves. It's the Beres-Wasserstein geometry. It's the space of all scaled and shifted. So you fix a base measure and you take all of the scalings and shifts of the base measure. So for example, in this definition, when rho is a Gaussian, then these are just all of the Gaussians with any mean and covariance. And perhaps surprisingly, this geometry does not depend on rho, or I should say, the metric only depends on the first two moments of rho. And so we make the assumption that it's centered and isotropic. And then you have one geometry that is really more so on the space of covariance matrices and means than it is on individual probability distributions. And this will be our simple, we think of this as the space of all neurons, or the space of all splats. So now I can give you a real definition, sort of the mean field splat model. So first we say that a splat measure lives in the space of distributions on RP cross Beres-Wasserstein. And if this is abstract, you can focus on the very concrete equation in the bottom. This is literally like, this is what is trained, is an empirical measure in this space. So this is for a p-dimensional output and a d-dimensional input.
What is rho here? Sorry.
Well, okay. In the first line, I should use different notation. In the first line, rho is a base measure. In the second line, when I sample rho, it scales and shifts of the base measure. So really it should be like rho prime.
Sorry, it was in the first slide you had a normal distribution. That was the rho?
Yeah. So
and how should I view it? Because in your comparison, sorry, maybe going back to your comparison with the MLP, because the output of the MLP is just the vector of the dimension of the output, but in the way you roll with the splat, it's a probability distribution.
So
or not?
We're using the functional form of the density of the distribution as an activation function.
Oh, okay.
So when I say that you have sparse activation patterns, it's because the supports of these first layer activations are not overlapping or have very little overlap.
Okay, so it's not like a probability distribution. It's really the function.
Right. I mean, similar to the mean field two-layer networks, we have a probability distribution representing the parameter space. And then a function is parametrized by the distribution. And in this case, instead of a distribution over, output vectors cross weights and biases for the input layer, rather it is output vectors cross probability distributions, because these distributions are our activations. Any other questions? Okay. I told you you'd be underwhelmed. Okay, we call the base measure, we call it a mother splat, sort of like a mother wavelet in the wavelet theory. And our perspective is that, I'm giving you all of these different ways to think about splats as activations or as um, uh, other like activation functions, probability distributions. We have now a third perspective, which is that they are smooth particles. So what I mean by that is that if I consider, a particle in Beres-Wasserstein, it's a little Gaussian distribution. And something that we were a bit interested to see in our calculations was that there's actually a concrete sense in which the dynamics for this model are sort of somehow like an averaged particle dynamics. And you can see this by comparing to splats with zero covariance is the idea. So it's an individual particle. Okay. I promise I will eventually get to experiments. The experiments will be of two types, actually three types. Two of them are, very roughly shown here. One is simple regression. So this is minimizing an L2 error of f of x minus y, where x and y are a coupling of training data. And then you would take an empirical approximation and minimize the risk. Alternatively, for inverse problems and solving integral differential equations, we imagine that you fix an operator, or script A, and minimize the residual error of the operator applied to the function. So it's regression and weighted regression in function space. Okay. This is my last background slide. This is another option for geometry that we can place on the space. So my intention was to explain some things about Wasserstein, and then I just also want to highlight that Wasserstein is not the only choice. This is a bit different from mean field theory of two-layer nets. To my knowledge, it is uncommon to study other geometries besides Wasserstein on the parameter space. But one of the directions that we're excited about is that by adjusting the geometry, you can create new algorithms. And this is when we say that we give a toolkit for algorithms, what we mean is that you put different geometries on the tangent space, and then they give you different algorithms, different optimization strategies. This one is Fisher-Rao. Here, in the Riemannian manifold picture, the Fisher-Rao geometry is the one which arises when you rescale mass. This is sometimes called teleportation. And so, for example, in the context of Beres-Wasserstein, maybe I teleport the weight of one neuron to another neuron, for example, to prune away useless neurons that are sparse too often. Okay. I'm going to show you the gradient expressions we derived. I'm not really expecting you to internalize these, but what this is our computation. It is for a generic functional. So like the examples of the functionals I showed, we compute how to we compute the Wasserstein and the Fisher-Rao gradients. I want to call your attention to the expectations in these expressions. This is what I mean when I say smooth particle dynamics, because here, for example, if we focus on the first line, the Fisher-Rao gradient, so the function depends on V, A, and V. These are the parameters of one splat and one output vector. The value of this function is, it says, should I add more mass or less mass here? If this function is positive, I add mass, I increase the presence of this neuron in the mixture. And if it's negative, I decrease the presence. And then this is computed by taking, in the first term, an expectation over the splat itself. and the same thing holds for all of them. If you take the limit as the covariances go to 0, you actually recover yet another geometry. It is that of the space. It's you recover the Wasserstein and Fischer-Rao geometries on RP cross RD. So you can imagine marginalizing over the splats. I evaluate a density on RP cross RD by just pointwise evaluation of this of the splat function. And you will have to take my word for it, but the geometry in this space is much nicer. And when you take splats with covariance approaching 0, you start to approximate a grid method in the classical sense. And so fitting with a grid method, if you solve regression on a grid, you're sort of just assigning vectors to each of the grid points. It becomes like a binning scheme. And this is roughly what we see in splats, except you can sort of anisotropically, heterogeneously, and adaptively choose how you perform the gridded interpolation. So it's very interpretable. Okay. We have some predictions, or I guess the hope for soon follow-up work is to understand how these different geometries actually lead you to specific heuristics. We also we're especially interested in an approximation theory for these functions. So I say which functions have small and everywhere sparse splat representations. So by this I mean like small k, very few splats, and very little overlap. And these are the ones which are highly efficient to perform inference or perform training. Okay. Now I'm going to spend a bit of time telling you about the experiments. So in the first one, this is an animation of training the model. So on the left, the function in orange is the target, and we're performing noiseless regression with, I think, 1,000 samples, which are the crosses. And then each of the tick marks on the axis are the locations of the splats. And so all of the output vectors are initialized at 0, and we're going to watch it train. Okay. And these are some snapshots. So what we see is, first of all, an initial phase where the splats sort of like find their location, and then very fast convergence as they as the output vectors sort of find the right value based on the location, very roughly. And what we're especially excited about is that when you compare this model to the performance of some existing sort of classical approximation schemes, it's actually doing surprisingly well. So in the plot on the left, first there are red baselines and blue baselines. The red baselines correspond to wavelet approximations of the target function in orange. And here, if you're familiar with wavelet approximations, there's a level of scale. So you this is a Haar wavelet approximation. So really it's like the L order Haar approximation is just constant on intervals of size 2 to the negative L. And we compare, we compute the MSE at these increasing levels of the wavelet approximation. Even, this is I guess I didn't write it, but this is a 90 parameter splat model, so 30 splats, 3 parameters per splat. And so we find this to be actually very impressive to fit, a rather difficult one-dimensional function with a 90 parameter model. Significantly better than Haar wavelets, which, okay, they're Haar wavelets. And there is as well the Chebyshev polynomial interpolation, which is if you think of 30 splats as being an interpolation of 30 grid points, then we're drastically outperforming a 30-point Chebyshev interpolation. However, by parameter counting argument, each splat has location scale value, Chebyshev has location and value. So if you equate the number of parameters, compare this 45, at least in this example, we see it, it's not uniformly beating everything. This is an even harder test case for an approximation theory. And it's very fast. I mean, it appears to be strongly convex and with very, very fast and stable convergence, again, in these toy examples. And here we're seeing very, very strong performance, again, relative to all of the baselines. So this is our first encouraging result. Now I'm going to move on to a slightly larger scale experiment. So this is on the scale that I would consider to be a baseline experiment in the physics-informed learning literature. So I'm just solving a simple 2D regression, and next I'll show you 2D PDE fitting. And in this case, we compare the Splat models, which are shown in blue. We compare many Splat models. I mean, I will tell you about the parameterizations of them. There's Splats in blue, multi-layer perceptrons, so ReLU multi-layer perceptrons in green, and then, in red. And in green, we have something called Kolmogorov-Arnold networks. So these were recently introduced about a year ago for solving some of these computational sciences problems. And what we see is similar to our approximation theory experiments. There's very, very, very fast convergence and typically drastically improved validation error, even at much smaller model sizes. So here the x-axis, well, actually, the left plot is the target function. The middle plot is the validation loss during training. And the right plot on the x-axis is the architecture size on a log scale. The y-axis is the validation error, also on a log scale. So we're really seeing like order of magnitude improvement on these two axes at the same time. In toy experiments, I want to stress that our immediate follow-up work is to scale this up. Right, and then I'm not sure, can you all read the little annotations? It's maybe not, but it's just a variety of parameterization in terms of the depth of multi-layer perceptrons, the depth of the Kolmogorov-Arnold networks. Obviously, Splat Regression is depth 2. And these brackets show you the widths of the layers. Okay. Any questions or comments? Our next experiment is like truly physics-informed learning. And here we use the Allen-Kahn equation, which is sort of a model for boundary formation. Here it's sort of a relatively large scale boundary just on one line in the domain. So this is a simple instance of Allen-Kahn equation. Our loss is a sum of residual errors. And so in order to perform training, we do two things. We sample interior points randomly, and we sample boundary points also randomly. We enforce the boundary condition at each of the sampled boundary points, and we enforce the PDE at each of the interior points. And crucially, there is never any observation of the solution on the interior point during the fitting. And so here, the optimization is a little bit harder. We see some like momentum effects, but for the most part, we see these similarly encouraging experimental results.
Just a question, these numbers in the brackets, those are the Ks?
So for Splat model, it is the K. For multi-layer perceptron, like when I say 20,20, this is a 3-layer neural network with 20.
Okay.
And I think these are, I mean, these are small networks, low dimensional problem.
And the dimension is 2 in this case.
Yes.
The actual.
Okay. It's good.
Okay.
All right, so I'm actually I went a bit too fast. I'm nearing the end. Maybe I add more of the theory for the next one. But we have positive preliminary results. We have a very simple theory of optimizing these networks. And I want to talk about what are the directions for going forward. First, I think to me, this is one of the most interesting directions is actually understanding the optimization phenomena that we see in some of these toy experiments. Our observation is that the log loss looks piecewise linear across multiple experiments. And so we think maybe there is some kind of like saddle point dynamics happening, and we think that it's related to the local behavior of each splat, as it sort of slowly finds its position and then quickly optimizes its value. So this is interesting to us. As well, I think we definitely need to prove finite particle approximation bounds. And I think that there is sort of an interesting direction to explore the interplay between training geometry and finite particle stability. I think to my knowledge, a lot of the existing propagation of chaos bounds in the mean field neural networks world is typically either for mean field Langevin dynamics or for mean field gradient descent dynamics, which is the Wasserstein geometry. It is unclear, for example, if the Fischer-Round geometry has nicer convexity properties and therefore nicer stability properties, for example. Right. These are more future directions. So one thing that we did prove in the paper is just simple, like very, very basic quantitative theorem for universal approximation. So I already mentioned that Saidenko's theorem holds, but what we showed is a quantitative version of this. So it is specifically a bound on the uniform approximation error, which is shown in the display, in terms of the width of the network. Now, in the second display, this bound applies to Lipschitz functions on compact domains. And if you think of, for example, a Lipschitz function on 0, 1 to the d, then one way that you can get an epsilon uniform approximation to it is by creating cubes of size epsilon, of which there are epsilon to the negative 1 over d. And so we believe that epsilon to the negative 1 over d is the optimal rate. Right now, we only know how to get the one which I've highlighted, which is worse by roughly sorry, this should be epsilon to the negative d, not 1 over d. So understanding the gap in these exponents is important. We think primarily for understanding the interplay between the smoothness of a function class and the mother splat that you should be using for that class. Again, we're trying to make analogies to wavelet theory, and so we would really like to understand, what which property in wavelet theory you have like cancellation of high order moments is the desirable property. We'd like to understand what is the desirable property for fitting smooth functions with splats. Right, as well, so there is I'm not going to expand on this, but there's another perspective for approximation theory and estimation theory for neural networks, which is the barren space theory. It is a sort of like it's not exactly, so the barren space is not exactly an RKHS, but it's kind of an RKHS that contains functions which are well represented by two-layer networks. And if you turn the crank on the construction with a different activation function, we're hoping to get a little bit of a simple picture of which functions, for which functions you can have dimension-free approximation. It would be the functions contained in the barren Splat space. And yeah, okay. Then this is my very last slide. It's more on the applied side, so the training heuristics. And I just want to make the point that in the experiments I showed you, in the experiments I showed you, training is performed in Wasserstein geometry. So it really is like training a two-layer network. There is not even the Fisher-Rao geometry. We experimented with it, but it wasn't necessary for the problem that I showed you. Yes.
I didn't really. Why is that? What would happen if, say, you would take the square laws and run just the gradient descent on the parameters? Like, is that the same? Or
It is the
what
same.
that actually means?
So it is the same. And the reason why is because like I said, that mean-field two-layer neural networks are trained with Wasserstein geometry. And in the same way, when we put Wasserstein geometry on the parameter space for splats, you recover gradients. Because you basically, like, in the space of measures, the direction of steepest descent for the function is the one that corresponds to the vector field that is pointwise the direction of steepest descent for each particle.
Which vector? When you refer to vector field, which quantity do you mean?
I'm thinking of a geometry on parameter space. And it is the vector field on parameter space is like the gradient vector field of the loss. This is not an obvious fact, but
very concretely, when you do the experiments, is it just a gradient descent on these B and A parameters and V as you introduced them at the beginning, or
yes.
Yes.
So in the approximation theory experiments, we like hard-coded the gradients and calculated everything. For the large-scale experiments, we actually literally use auto differentiation for the parameters. So then the difference, I guess, is
So why do I need to then think about these like alternative interpretations of that?
Well, there's two reasons. One is that, like, while we are training the parameters with gradient descent, remember that the appearance of the parameters in the neural network, I'm looking for, okay. So here, I could tell you that we're doing standard gradient descent training of a vanilla neural network, but we invert the weight matrix. Like, this is the prescription that you get from the Wasserstein geometry. So I just mean to point out that there is some prescription for the algorithm that you get from this choice. And for Fisher-Rao, a phenomenon that has been observed, for example, in mixture modeling. So mixture modeling, if you just remove RP and you take the mixtures of splats, gradient descent algorithms in this space have been widely explored for problems like variational inference. And there it is provably the case that the Fisher-Rao geometry is favorable for optimization. In other words, you have like, I don't want to say something that's not true, so I'll just be vague and say that you have improved convexity properties of the loss in Fisher-Rao geometry. And it's somehow because when you're transporting particles in, let's say, 1 dimension or 2 dimensions, you can't have particles following trajectories that cross roughly, because they're drifting in a vector field, and so if they ever cross, then they just stay coupled forever. And in Fisher-Rao, you somehow have more freedom because you can take any point you want, regardless of neighboring points, and you can scale the mass up or scale the mass down. So somehow it's a little easier. Yeah. It's also, each of these geometries comes with discretization algorithms Right, each includes discretization algorithms, and in the literature for particle methods, you can make comparisons between something like approximation of Fisher-Rao dynamics versus like optimization heuristics used in Gaussian spotting. And you can say, well, you know, we know that this Wasserstein geometry alone is not enough to solve the Gaussian spotting problem. And this is coming from the fact that the heuristics that they use, like teleporting particles, is essential to fitting these like large and very sharp models. And so the hope is that there can be some kind of like positive interaction between the particle methods community and the heuristics that are developed for this like sort of poor person's particle method. Poor person's particle optimization in the Splat world. And we think the lens to do this is through different geometries on the parameter space.